Let's derive some Taylor series. The formula is this one. If a is equal to 0, we will have a more simple formula. In this case, the series is also called the Maclaurin series. If our function is the sine of x, we can fill this table. The derivatives of sine will be the zeroth derivative is the function itself, then we have the cosine, then we have minus sine, then minus cosine, and then again sine of x. The derivatives will have the value at 0 equal to 0, 1, 0, minus 1, and so on. We will obtain at first 0, then plus 1 times x to power 1 divided by 1, then 0, then minus 1 times x to power 3 divided by 3 factorial, and so on. Sine of x is like this, and we obtain this formula. If our function is the exponential function, the things will be even more simple. All the derivatives will be equal to power x, and all the derivatives in 0 will be 1. So we obtain our series and a formula. By using the formula of Taylor series, we obtain the expansion for sine of x and e to power x. If we take the expansion of sine of x when we differentiate it with respect to x, derivative of sine of x will be cosine of x, and by differentiating term by term, we will obtain the series for cosine of x. The hyperbolic sine is defined to be e to power x minus e to power minus x divided by 2. By using the expansion of e to power x, we can write the expansion of e to power minus x. We find out that if we sum these, then every other term will cancel out. So for this function here, we would obtain something like this. But I made a mistake. I'm getting now the hyperbolic cosine because I have here the plus sign. Well, hyperbolic cosine will be equal to this series, and hyperbolic sine will be equal to this series. So we obtained the formulas for the hyperbolic cosine and the hyperbolic sine, and we can see that these functions are looking quite similar. So I think that's the name for reason why their names are similar. Next, we know that the geometric series has this sum. If we take this formula and we differentiate on both sides, we would obtain in the left this kind of function, and in the right we would obtain this series. On the other hand, we want to integrate this side by side. We find that the derivative of this function is equal to the sum of the geometric series. So by starting from the geometric series and integrating on both sides, we obtain the series expansion for this logarithm. If here we would replace minus x by plus x, we would have to put a minus sign to the right side also. And we can write the right side in a little bit different way. Like this. And if we go for this minus sign, we can take it off if we just put a plus 1 to the right side. If we would take now these functions and sum them together, we would obtain this function. Its series will be the sum of these series, and we will have the same thing as with this e to power x and e to power minus x, that if we sum these together, some of the terms will cancel out. We obtain this formula. You can find these formulas from the Glynn-James Modern Engineering, page number 517 in the 6th edition.